As we know, solving for the wave function of an atom or an electron means understanding the full atom, including all of the electrons in it and the nucleus. And that means working with the Hamiltonian for that system. And as I said in the last lecture, the Hamiltonian that we described in our previous lectures focused only on considering just one electron about a nucleus. And even as we add in extra electrons, we're considering the central field, which is just the field that has the Hamiltonian put together of the kinetic energy of the electrons plus an interaction between that electron, any given electron, and the nucleus, and then some interaction between the electrons themselves. And all of that describes the underlying electrostatic potential of the whole system. But that's not quite it, because that neglects the spin terms, and that neglects how those interact. The orbit and the spin interact with each other. And that adds yet another component to the Hamiltonian that we need to bring in before we can describe a wave function. Now, yet again, I don't want to go through the details of the mathematics of that, but simply to raise it into your awareness so that you recall how it can be difficult to decide which energy levels an electron is allowed to go into and which it cannot. And that it's all about trying to minimize the difference in the energy. So let's just have a quick think about this. So if you recall that the Hamiltonian for a many electron system would be written out in terms of the zeroth order central field Hamiltonian plus some perturbation. So the zeroth order central field, and this one here is a perturbation. And the zeroth order field is made up of something that has to do with the kinetic energy of the electrons plus something that is an attractive Coulomb interaction between electron and the nucleus, and then some repulsive Coulomb interaction between electrons. But we need to now bring into it something else which adds to this perturbation. So that's the extra term, which brings in the coupling between spin and orbit, as well as more information about the individual electron repulsions and electron smearings. So we can bring in a perturbation term which has an electrostatic component and a spin orbit component. And the electrostatic component includes the electron smearing of the potential, and the spin orbit coupling comes in. So how does this play out? Well, consider just spin for the moment. So for spin, remember that the spin of a system is the sum of the individual spins for each electron. And if the spin is large, that tells us that the particular individual spins must be preferentially aligned. So if they're both, they might be something like up and up would be preferentially aligned, then the electrons have to reside far apart because of the Pauli exclusion principle, which says that they can't occupy the same orbital. So the energy due to the electrostatic repulsion is going to be lower. So let's just write that out. So if S is large, then that spreads the electrons apart so that the electrostatic repulsion energy will be lower, and that reduces the entire energy of the system. And that is called Hund's rule number 1. Terms with larger spin have lower energy. So that's the first one. You can consider the orbital angular momentum as the other one. So the orbital angular momentum, which is defined as L equals the sum over I of all the electrons of the individual orbital angular momentums. So in this case, if L is large, that tells us that the angular momentums, individual angular momentums are aligned. And so the electrons must be orbiting the atom in a similar pattern. And that means that the electrons are kept far apart, and therefore the energy is lower. And that is Hund's rule number 2. Which says that terms with larger orbital angular momentum L have a lower energy. Now, these rules apply only to the ground configuration, but they are helpful ways of separating out the different energy configurations for a ground configuration. And we'll stop there and pick up